Elements, Compounds and Mixtures by Dr. Abraham Chidize Nicholas. That is the topic we are going to be talking about today. We would look at the different elements we have in nature, what are compounds, what are mixtures. We'll look at chemical symbols of these elements, how they are derived and their classification. We'll also try to look at what radicals are, valency, ions, and other things in the course of this presentation. Now, I would like to start by defining what an element is. An element is a substance which cannot, by any known chemical means, be split further into two or more simpler forms or substances. So it's trying to tell us that an element can be broken down into something else. And in nature, we have about 106 elements. Examples include hydrogen, helium, calcium, sodium. There are so many of them, like I said, about 106. Now, a compound is a substance that contains two or more elements which are chemically combined together. Examples include water, common salt, etc. Your water contains hydrogen and oxygen, which are two different elements. Your common salt, which we use in cooking, the scientific name, which is sodium chloride, contains sodium and chlorine. So these are examples of compounds that we have, while a mixture consists of two or more different substances or elements that are physically combined together but separated chemically or physically. So that's like a distinguishing feature between the compound and the mixture. For the mixtures, you can combine them physically, but when you want to separate them, you have to separate them either chemically or physically. But for compounds, their separation technique or separation system is only done via chemical means. Now, examples of mixtures we have include soil. Soil is a mixture of different particles. You have your urine, you have seawater, you have milk. Now, we also have two types of mixtures. We have a heterogeneous mixture and a homogeneous mixture. I'll start with the homogeneous mixture. Now, a homogeneous mixture is a mixture that is uniform. You won't be able to separate the two different components that make up that mixture. A typical example is when you dissolve sugar in water or when you dissolve salt in water. At the end of the day, the salt solution or the sugar solution you have is uniform. When you look at it, you won't be able to tell whether sugar was dissolved in that water or whether salt was dissolved in that water. So that is a type of a homogeneous mixture. While a heterogeneous mixture is a mixture that has clearly distinct separation or distinct layers. You can tell by looking at it that you have two different components or you have three different components within a particular solution or within that mixture. Example, a mixture of maybe fuel and water or kerosene and water. These are examples of heterogeneous mixtures because you can clearly see the distinct layers or you can clearly see the distinct difference between the different layers. Now, chemical symbols of elements. Now, these are letters that are used to represent elements in whatever state that they may exist. They are a form of shorthand. For example, people who have long names like Tam Nongaribika can have them shortened to Tam. If your name is Abraham, they can decide to call you AB or Adebayo or Ade. These are shorthand forms of people's name if you don't want to call the full thing. So the same thing applies to these elements. We use chemical symbols to shorten the way we represent them. Instead of writing their names in full, we decide to use symbols that are derived from either their names in English or their names in other languages like Latin, Arabic, or even Greek. Now, these elements are classified into four categories depending on the manner in which the symbols were derived. Now, the first class of elements are those that their symbols are derived from the first letter of their names. Example, hydrogen, the symbol is H, oxygen is O, nitrogen is N, phosphorus is P, sulfur is S, iodine is I, fluorine is F. So these ones, their symbols were derived from the first letter of their name. Now the second class, these elements derive their symbols from the first two letters of their names. Example, helium, He, lithium, Li, beryllium, Be, silicon, Si, argon, Al, calcium, Ca, radium, Ra. Their symbols are derived from the first two letters of their names. Now, for the third class, the elements in this category have their symbols derived from the first and third letter of their names. Example: zinc, Zn, arsenic, As, magnesium, Mg, manganese, Mn, chlorine, Cl, rubidium, Rb. Then for the fourth class, the symbols of these elements are derived from their names in other languages. Example: potassium is called kalinum in Arabic, the symbol is K. Copper is called coprum in Latin, the symbol is Cu. Lead is pugmentum in Latin, and then the symbol is Pb. Iron is ferrum, also in Latin, symbol Fe. Mercury is hydrogenum in Greek, and the symbol is Hg. Now, I want us to note that if you've observed from the way I've been writing the chemical symbols, the first letter of the symbol of any element must always be in capital. Then for those that have two letters as their symbols, the second letter must then be a small one. So it is important for us to note that the first letter must be a capital letter, and then for those that have two letter symbols, the second letter must be a small one. Now, at this level, our focus will be on the first 20 elements. So it is paramount that you need to know the first 20 elements according to their number from 1 till the 20th. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. Now, why I said you need to know the proper arrangement from 1 to 20 is that the arrangement from 1 to 20 is equivalent to the number of atoms each of these elements have. Hydrogen is the first element, it has 1 atom. Helium, the second element, it has 2 atoms. Sodium, the 11th element, it has 11 atoms. Chlorine, the 17th element, it has 17 atoms, which we also call the atomic number. So that is why it is very important for us to know the proper arrangement of these elements from 1 to 20. And even when you get up to the senior class, your focus will still be on the first 20 elements. Even if you get to learn about the other elements, it will be in a passive state, just nothing too concentrated at this level. Now, the next thing we'll talk about are radicals. These are a group of elements that tend to behave as one. For example, we have hydroxide, symbol OH, with a minus sign at the top. The minus sign there is like is the ionic, what we call the ionic charge. Now, it is a radical that comprises of hydrogen and oxygen behaving as a single atom. So in this state, they are no longer hydrogen and oxygen, but hydroxide. Now, other radicals we have includes trioxonitrate 5, tetraoxosulfate 6, trioxocarbonate 4, ammonium. Now, these radicals react with other elements to form compounds. So, for example, hydroxide that we have there can react with sodium to form sodium hydroxide. It can react with magnesium to form magnesium hydroxide. Trioxonitrate 5 can react with sodium to form sodium trioxonitrate 5. Tetraoxosulfate 6 can react with hydrogen or potassium to form hydrogen tetraoxosulfate 6, which we know as an acid, or potassium tetraoxosulfate 6. These radicals have the ability to react with other elements, but in these states where they behave as one. We no longer consider them to be two different elements that make up the radical, but they act simply as one. Now, radicals, like I said earlier, do not stay alone but combine with elements to form compounds. Now, we need to know that when a compound is formed, the molecules have no charge. That is, the negative charges on the ions of one element must balance the positive charges on the ions of the other elements, so they cancel out each other. So what we have here now is sodium ion reacting with trioxonitrate 5 ion, which is a radical, to form sodium trioxonitrate 5. Now, in this state, this is hydrogen ion reacting with tetraoxosulfate 6 ion to form hydrogen tetraoxosulfate 6. Now, if you observe the products that are formed, you cannot see any positive charge or a negative charge at the top. These are compounds, they have no charge. These are molecules, they have no charge. But the ones that have the charges are the ions and the radicals. Now, the next thing we'll talk about is valency. Now, valency is known as the combining power of an element. It is what helps two different elements to combine together to form a compound. Now, it is also known as the number of electrons that could be gained or lost by an element. Now, in the course of this, what we have here is called the electronic configuration of elements. Now, electronic configuration is simply showing the arrangement of electrons of different atoms in different shells, or what we call orbitals. Now, we have two systems of electronic configuration. We have the KLMN system, and then we have the SPDF orbital system. But for the purpose of knowing the valency of these elements, the most preferred one is the KLMN system. With this, you'll be able to know the valency of these elements without having to cram it or trying to store them up in your head, when you can just simply produce the electronic configuration, and from there you get your valencies easily before writing any examination. Now, for the K shell in this orbital system, the K shell contains a maximum number of 2 electrons. The L contains a maximum number of 8 electrons. The M and the N also contains a maximum number of 8 electrons. Now, I'm going to show you how these electrons are arranged in the different shells first, before we proceed to how we can get the valencies from them. Now, we'll start with hydrogen. Hydrogen is the first element. So the atomic number of hydrogen is 1, since it's the first element, and the number of electrons of hydrogen is also 1. So that 1 electron goes into the K shell. For helium, helium is the second element. Atomic number is 2, number of electron is also 2. So that 2 also moves into the K shell. So meaning the K shell for helium is complete. But when you now move down to lithium, which is the third element, it has 3 electrons. So the moment you put 2 electrons in the K shell, the extra 1 electron automatically moves to the next shell, which is the L shell. So for example, let's say we have 50 students who want to admit into JSS 3, and then we only have 2 classes in JSS 3, JSS 3A and B, and then 3A can only house or contain 30 students. So the moment we put 30 students out of the 50, it means that the remaining 20 students automatically will move into JSS 3B. So that is the same way this electronic configuration progresses in terms of the arrangement of the electrons. The moment a particular shell has taken the maximum number it can contain, and there's an extra one, that extra one will move to the next shell. So beryllium is the same thing, 4th element, atomic number 4, 4 electrons, 2 we put in the K shell. The K shell is complete, so the remaining 2 automatically moves to the L. Carbon, 6 electrons. The moment you put 2 in the K, the remaining 4 goes to the L. So you proceed that way till you get to neon. Neon is the 10th element. It has 10 electrons. 2 will be in the K. The remaining 8 moves to the L. But when you now get to sodium, that has 11 electrons, the moment you put 2 of those electrons in the K, you're left with how many? That's 9. Now, out of the 9, the L can house 8. So 8 of them comes in there, and then the remaining 1 automatically moves to the M. So we have 281 as the electronic configuration for sodium. You keep through the same system, 282, 283, 284, until you get to argon again. Argon is the 18th element, so the arrangement is 288. Now when you get to potassium, which is the 19th element, 2 comes into the K, 8 moves into the L, another 8 moves into the M, and the remaining 1 moves to the N. So this is just how you arrange the electrons into the different shells. So now the next thing we'll move into is now how do we now get the valency after we've written all these things we have on our screen. Now, we described valency as the combining power of an element, and we also said that it is the number of electrons that can be gained by an element, or the number of electrons that can be lost by an element. So now, for us to get the valency, basically, we are trying to obey what we call the octet and the duplet rule. Duplet meaning 2, octet meaning 8. What the rule is trying to tell us is that every shell must be complete in order for it to attain stability. Now, looking at hydrogen, our concentration is going to be on the outer shell of these elements. Now, looking at hydrogen as a starting point, hydrogen has 1 electron in the K shell, which is the only shell that it has. So that's the outer shell for hydrogen. Now, it can either gain 1 more electron to make that 1 to become 2. So because hydrogen is gaining 1 electron to complete its outer shell, the valency of hydrogen is 1. For helium, the outer shell is already complete. Now, if you observe, I highlighted 3 elements here in black. Helium, outer shell is 2, is complete. You go to neon, 2, 8. The outer shell is also complete, 8. And then you go to argon, the outer shell in the M is also 8. Now, these 3 elements, helium, neon, and argon, are known as inert gases or noble gases or rare gases. You will never see them in any chemical reaction. You will never see them react with any other thing because their elements, the number of electrons that they have are complete. They are already stable. They are obeying the duplet and the octet rule. For helium, it is obeying the duplet rule because in the outer shell, it has a maximum of 2. For neon and argon, they are obeying the octet rule. They have 8 electrons in the outer shell. But for these other ones, you can see that the outer shells are not complete. So meaning we need to look for a way to make them to be stable. Now let's move down to lithium. Lithium is the third element, 3 electrons. On the outer shell, it has 1 electron. So meaning for this outer shell to be complete, it either has to gain 7 electrons that would complete the L shell to be 8, or it has to give away this 1 electron so that it will be left with just 2. If it is left with just 2, that's a complete shell, is it not? Because the K shell, we said, contains a maximum number of 2. So now let's go back to this L. Now imagine a scenario whereby I send Obi to go to Rumokoro. From Rumokoro, he goes to Rukpoko. From Rukpoko, he goes to Igurita. From Igurita, he goes to Elele. From Elele, he goes to Owerri. From Owerri, he goes to Onitsha. From Onitsha, he goes to Asaba. 7 different places. He's going to spend more energy, is it not? And say I send Ada to go to the talk shop, and then she comes back. Who spends more energy? Obviously, it's Obi, because he's having to go longer distances. He's spending more energy. He's consuming more energy. So the element lithium will spend more energy trying to gain 7 electrons to complete this outer shell than if it was to give away this one. So because it is easy for lithium to give away this 1 electron than to gain 7, the valency of lithium is 1. Because it spends lesser energy. The same thing applies to beryllium. It has 2 electrons in the outer shell, meaning it either has to gain 6 to complete this 8, or it gives away this 2. It is easy to give away the 2 than to gain 6, so the valency of beryllium is 2. Let's move down to oxygen. Oxygen has 6 electrons in the outer shell. For that outer shell to be complete, it either has to gain 2 electrons to complete its 8, or it gives away the entire 6. Now, it is easy for it to gain 2 than for it to lose 6. So because of that, the valency of oxygen is 2. Fluorine, the same thing, 7 electrons in the outer shell. It is easy to gain 1 electron to complete this 8 than to give away this 7. So because of that, the valency of fluorine is 1. Let's move down to potassium. Potassium has 1 electron in the outer shell in the end. It either has to gain 7 to make this 8, or it has to give away this 1. So it is easy to give away 1 than to gain 7. So because of that, the valency of potassium is 1. For calcium, the same thing, 2 in the outer shell. It is easy to give away 2 than to gain 6 electrons that will make this 8. So because of that, the valency of calcium becomes 2. Now I want to paint another scenario for you. Now in your last well, you might have come across a question. They might ask you, sodium atom has 11 electrons. Since sodium is 11th element, like I said, it has 11 atoms, meaning it has 11 electrons. So if sodium atom has 11 electrons, sodium ion has how many electrons? How many electrons will it have? Sodium Na with a positive sign on top. Now that positive sign is indicating that that is an ion, sodium ion. So that positive sign there indicates that there is a loss of an electron. Whenever you see any elements carrying a positive sign at the top, it means that there is a loss of electron. If it is carrying 2 and a plus, it means there's a loss of 2 electrons. Like in the case of magnesium, you see magnesium written as Mg raised to power 2 and a plus sign by the side of the 2. That means that there is a loss of 2 electrons. Aluminium, the same thing, you see aluminium written as Al3+. Now that plus sign on top is also, or a minus sign on top, is also indicating the valency of that element. That is another trick of knowing the valency of an element. Now back to the question that I asked, if sodium atom has 11 electrons, sodium ion will have how many electrons? And probably in the options you have maybe 11, you have 10, you have 9, you have 8, 4 options. Now the answer is 10, because by the time sodium loses 1 electron in the outer shell, it will be left with what? 2 and 8. 2 plus 8, that is 10. So meaning sodium atom has 11 electrons, but sodium ion has 10 electrons. If it was in the case of, let's say, chlorine, normal chlorine is 17. It has 17 electrons. And then they said chloride ion has how many electrons? Remember we said here that chlorine in the outer shell has 7 electrons. So because it has 7 electrons, it is gaining 1 electron to complete it. So since it is gaining 1 electron, it means that chloride ion has 18 electrons. Normal chlorine, 17 electrons. Normal chloride ion will be 18 electrons. Now, earlier I said if an element is carrying a positive sign, it means that there is a loss of electron. But in the case of chlorine, where there is a gain of an electron, it will carry a negative sign. So anytime you see any element carrying a negative sign at the top, it means that there was a loss of electron. There was a gain of electron. If it is carrying a negative sign, there was a gain of electron. But if it is carrying a positive sign, it means that there was a loss of electron. Now the next thing we'll be moving to, we'll be talking about ions. Now it says ions are charged particles that are formed as a result of the gain or loss of electrons by an atom, and they are of 2 types. We have the cations and we have the anions. Cations are positively charged ions. Example, we have sodium ion, we have calcium ion. And like I said, this plus sign is also indicating that the valency of sodium is 1. The 2 plus here is indicating that the valency of calcium is 2. So it is also indicating that there was a loss of 1 electron. That is why it's carrying a positive sign. And then the anions are negatively charged ions. We have chloride ion, meaning there was a gain of 1 electron since it is carrying a negative charge. And then the note there says when an element loses an electron, it becomes a cation, but if it gains an electron, it becomes an anion. Thank you and see you in the next class.